I've asked Ania to come and talk about some work that she is doing at Nym. The Interchain Foundation also has a grant with you guys to develop this as a general purpose Cosmos SDK module. So we're hoping this becomes a piece of public infrastructure that other Cosmos chains can deploy. And this is kind of complementary to the work that you're doing at Nym. So it helps. Nym is a state-of-the-art mixed network, and it uses Tendermint to ensure mixing quality and service provision. So we thought this kind of paired well with the talk, or the workshop that Chris will be giving after Ania's talk. And he's going to be talking about multi-chain shielded pools that are based on a Zcash circuit design. And we're hoping to potentially fold in maybe insights from your conversation into Chris's discussion. Chris works at Interchain GmbH here in Germany. He's a colleague of mine. And he's also the co-founder of Metastate, which has a focus on cryptography. And Chris, notably, Chris is the lead protocol designer of the Interchain interblockchain communication protocol, which ensures the kind of primary feature of IBC is to ensure kind of fault isolation between different chains. And we think this is particularly well suited to developing and deploying new cryptography. So I hope that Chris kind of inflects that and describes how that can that property can be retained with shielded assets. And for Chris's session, he's gonna give a short intro to kind of frame the problem and then open it up for discussion. So please put your questions in the chat. And I will get rid of my audio and video and hand it off to you, Ania. Thank you.
Great. Thank you so much. Let me now try and share my screen. Give me a second.
And let me know. I'm also here. I just turned off my video so people don't just watch. But if I'm happy to read questions off the chat, you can read them if you'd like. If you have a second monitor, or Sam, you can feel free to as well. So again, if you guys need to leverage me at all, I'm right here. I'm just going to turn off my audio and video.
Sure. Quick question: can you guys see my presentation? Did the screen share work?
Yes.
Great. Okay, so hello everyone. My name is Ania Piotrowska. I work as the head of research at Nym Technologies. Nym is a company which is building a decentralized and incentivized communication infrastructure or network to give the internet users privacy. And during today's talk, I will introduce you an outline of two main components that Nym is using. The first one is the Nym mixnet. The Nym mixnet is used to ensure the network level privacy for the users. The second component, which I'm going to present you, is the Nym credentials, which are the anonymous selective disclosure credentials, which in very simple words allow you to anonymously prove that you have a right to access certain service or to use a certain service and so on. So let's dive into it. So let's start with the Nym mixnet. Why, in general, do we need network level privacy? So if you're into privacy, you are probably familiar with applications like Signal, Telegram, WhatsApp, maybe protocols like PGP, which you probably use to encrypt your communication. So such applications or protocols like PGP allow for the end-to-end encryption, which means if you're sending a message or any type of communication, you can protect the content of your communication. So the end-to-end encryption gives you confidentiality. Or maybe, for example, you're interested in cryptocurrencies and you want to use them, but you want to use them in more privacy-preserving ways. So you might be using Monero, Zcash, maybe some coin tumblers, maybe the Lightning Network. So such private coins or the techniques which enhance the privacy of coins give you privacy on-chain. But both end-to-end encryption and any on-chain privacy techniques, they don't give you privacy at the network level. What it means, if you have the adversary who is observing the flow of the packets in the network, he'll be fully able to de-anonymize you. So he will just observe which IP address is sending a message or transaction to which other IP address, and that's how your privacy is broken. And this is very important because privacy is a bit of like a holistic property. If you have a system, if you're leaking information in one layer of the system, doesn't matter how fancy cryptography or encryption schemes you're using in the other layer of the system, the leakage in one layer will undermine the privacy properties which you're having in different layer. So how can we protect the network level privacy? The Nym is using a mixnet for that. And what is a mixed network? Mixed networks are around already for quite some time. They're pioneered by David Chaum in the 80s. And a mixed network is just a set of cryptographic relays which process and forward the packets. And the traditional mixed networks was just a multi-hop network in which the mixed nodes were arranged into a topology to which we refer as a cascade. So they created like a long chain, and the packets were flowing from the first to the second, third, and so on mixed node. So the packets were flowing through the whole cascade. And how the mixed network protects your network level privacy. So when you're sending a packet via the mixed network, it's layer encrypted, or as we refer to it also, onion encrypted. What it ensures is that if I'm the adversary and I'm observing the flow of the packets in the network, I cannot correlate those packets based on their binary representation, because after each mixed node, the binary representation of each packet is changing. So what it gives you is something to what we refer as bitwise unlinkability. So we cannot correlate the packets based on their binary patterns. But protecting the binary representation or hiding the binary representation of the packets is not enough to actually give you anonymity at the network level, because the adversary can still perform the timing analysis, which means he can just observe the mixed nodes, and if the mixed nodes are processing the packets at the first in, first out order, what happens is that the adversary can correlate the incoming and outgoing packets. So at the end, although your packets will go via multiple hops, the adversary will be still able, based on the times he observed the packets coming in and out, to correlate who is communicating with whom. And that's why the mixed nodes protect against such timing analysis. What happens is that a mixed node, each one of them in the cascade, instead of forwarding the packets at the first in, first out order, what they do is they instead of batch the packets. So what happens is that a mixed node is running and he is waiting for a certain number of packets to arrive, let's say 1,000. So he's waiting for 1,000 packets to arrive, and once he gathered 1,000 packets, what he does, he is processing them cryptographically. So he removes this like one layer of onion encryption, and then he shuffles them following a secret permutation and forwards to the next hop. So what happens right now is that the adversary cannot correlate the packets neither based on their binary representation, neither based on the timing of the packets. And what the mixed network ensures is that you're anonymous at the network layer, even if the adversary is able to observe all the links between the mixed nodes. Moreover, you're also fully anonymous if all the mixed nodes except one in the cascade are dishonest. So as long as one mix is honest, you're anonymous. So you might ask, why, although the mixed network gives you such a strong anonymity, we actually don't have any mixed networks deployed? Like, how this happened? So as it turns out, the early Chaumian mixed networks had a few very severe limitations. The first one was scalability. As you can probably imagine, the cascade topology doesn't scale good. So the only way to scale your cascade is to make your mix nodes more and more and more powerful, which means for the people who are running the mix node, just pay more for the servers and pay more. So this obviously doesn't really help to deploy the system on a large scale. The second limitation was that the mixed networks imposed very, very high latencies. And for those high latencies, there were two reasons to happen. First one was that the onion encryption scheme used by the traditional mixed networks was using the public key cryptography, which is quite expensive. The second reason why the traditional mixed networks had very high latency was that the batch and reorder mixing techniques, which the mixed nodes were using, were imposing very high latencies. And you can think about it intuitively in the sense, let's assume your batch size is 1,000. And now the volume of traffic in the mixed network is low. What it means is that mixed node will wait a very long time to gather those 1,000 packets. So automatically your latency at each mixed node and then your end-to-end latency will be much higher. But even if the volume of traffic is large, still your latency, the end-to-end latency at the mixed network will be also large because all the packets are coming very quickly. You process the batches one after another. So a lot of packets will be queuing to get into another batch and be processed. So the high latency made mixed networks completely unusable for any applications which are latency sensitive. And the third limitation of the traditional mixed networks was that the anonymity size offered by the mixed network was limited to the size of the batch in each mixed node. So again, if your batch was 1,000, it doesn't matter. Even if you had 5 million users using the mixed network, you are anonymous only among those 1,000 packets with which your packet was mixed in the batch. And also, as research showed, the traditional mixed network were vulnerable to the traffic confirmation attacks and to active attacks. The traffic confirmation attacks are those attacks which some of you might know from Tor, when the adversary is controlling or observing the entry and exit node, and he can observe the sending and receiving patterns of the users, and based on that, he can correlate the flows. So how Nym is fixing those problems? Let's start with the scalability issue. So instead of using the cascade topology, Nym is using the stratified topology. A stratified topology is a topology in which mixed nodes are grouped into layers. And each mixed node from one layer, the first one, is connected with each mixed node in the second layer, and then each mixed node in the second layer is connected with each mixed node in the third layer, and so on. So the traffic is flowing always from the first to the last layer. And the advantage of this topology is that it scales horizontally, meaning by adding more and more nodes, you can increase the overall capacity of the network. And obviously, when you're building an anonymous communication network, you want your network to scale because anonymity loves company. So the more users you can support, the better. And actually, the stratified topology was shown to be optimal for scalability and anonymity. So out of all the possible topologies which you can consider, like cascades or multi-cascades or peer-to-peer, the stratified topology is the best. And the packets in Nym are source routed, meaning that the sender picks the path which the packet should take. And the sender does that by picking randomly one mix from each layer. So that's how he composes the path. Okay, so once we cover the scalability issue, let's look into the latency. And that's much more complicated problem. Now we have here two things. First of all is the onion encryption and how can we make it a bit faster. And the other is the latency, which is imposed by the batch and reorder mixing technique. So at Nym, for onion encryption, we use the Sphinx cryptographic packet format. Some of you might know it from, for example, the Lightning Network. It's a provably secure cryptographic packet format, which not only ensures that the packets are bitwise unlinkable and they're the same size all the time, it's also very compact and very computationally efficient, which means the processing or creating of the packets is much faster than it used to be in the traditional mixed networks. And on top of that, Sphinx also gives you a few properties which are very important. Like, for example, it gives you resistance to tagging attacks and replay attacks. So these are attacks in which the adversary try to, for example, tag a packet to be able to trace it later in the network, or tries to enforce the user to send multiple times exactly the same packet to try to, increase his chances to de-anonymize the user or de-anonymize where is he sending. And another important property of Sphinx is that the intermediate nodes which are processing the packet learn only the predecessor and the successor. So they only learn from whom they receive this packet and to whom they have to send, but they're not learning any other information about the path or about the sender and receiver. So that's the first part. We've made a choice to use Sphinx to make the cryptographic operations much more efficient and to not in such a way that they don't impact negatively the overall latency in the system. But what about the mixing technique? So I told you that the patch and reorder mixing technique had this problem that the end-to-end latency was unbounded. The user had no control over how long it will take for his packets to, get to the destination. So that's why Nym uses something what we refer to as continuous time mixes. And what it means, it's simply that instead of batching the packets together, each mix delays each packet independently before forwarding it. So how it works is that if I'm the sender and I want to send a packet, for each mix in the path which I selected, I also pick a random delay. And this delay is drawn from the exponential distribution. And once I've picked those delays, I put them inside the Sphinx packet format so that when the mix node receives the packet and strips one layer of encryption, he can see the delay so he knows how long he should keep the packet before forwarding it. And using such mixing technique has two important properties. First of all, because the sender is picking the delays, I, as a sender, can estimate the end-to-end latency of my packet. So I know how long it should take my packet to go through a network, assuming that there is no congestion, right? Another advantage is that because I control the delays which I pick, I can adjust the end-to-end latency which I would like to achieve depending on the application for which I'm using the Nym mixnet. And how it works is that there's a bit of math behind that, but it's very simple. The average delay which the exponential distribution will give you is determined by the mean parameter of the exponential distribution. So you can tune up and down depending on your application or service, this mean parameter. So either your delays, which you're picking still randomly, will be lower or will be higher. But it gives the senders the control to really control the end-to-end latency. And because of that, the Nym mixnet can support applications or services with very different latency constraints. Okay, so we covered this scalability, we covered the high latency. Let's look a bit closer into the anonymity. So I told you that in the traditional Chaumian mixnets, your anonymity is limited by the size of the batch which the mix node is using. So how do we solve that problem at Nym? Well, it also boils down to the mixing technique. I told you that when the sender picks the random delays, he's using the exponential distribution. And we pick this distribution for a reason. The exponential distribution is actually the only continuous distribution which has a property called memorylessness. What it means that the past has no bearing on the future. So in simple words, imagine that packets are arriving into the mix node, and you're the adversary, and you observed, let's say, 10,000 packets arriving to the mix node. And now one packet is leaving. What happens here is that from the perspective of the adversary observing the mix node, this packet, which is just exiting the mix node, with equal probability can be any of the packets which arrive to the mix node. So the ones which you observed arriving to the mix node. This is because the time at which the packet will leave the mix node from the perspective of the adversary is completely independent on the time when the adversary observed this packet arriving. So what it gives us? It ultimately tells us that your anonymity set is not anymore bounded by the size of the batch. Your anonymity set can be much, much larger because now each packet coming into the mix node contributes to the anonymity of your packets. And this is very important because what our study shows is that while in the traditional cascades, the size of the batch was determining your anonymity, and it doesn't matter how many users are using this mixed network, at Nym it's different. The more users are using the mixed network, the better the privacy properties. So you can see it on this simple plot, which I did. You can see that while the number of users is growing up, the anonymity in the Nym mixnet is also going up, whereas in the cascade topology, which is using the patch and reorder technique, it remained all the time constant, and there's nothing you can do about that. And the last limitation which the Chaumian mixnet had was that they're vulnerable to traffic confirmation attacks and active attacks. And this is quite a serious problem because users tend to have very distinctive behaviors and sending or receiving patterns. So based on that, the adversary would be able very quickly to de-anonymize the user. So how do we protect against that? Imagine the adversary who observes the entry and exit points of the mixed network, and he sees a sudden burst of packets from Alice. And at the same time, suddenly Bob starts to receive many more packets. Probably you can correlate that Alice and Bob are communicating. So in order to protect against that, the Nym client uses something what we refer to as Poisson process to schedule packets to send. In a nutshell, how it works is if I want to send a message and I click on my application the button send, the Nym client, instead of immediately sending this packet, it adds it into a buffer. It's an internal buffer which it works like a queue for the packets which are scheduled to be sent. And in the background, there is a Poisson process running, which from time to time checks this buffer. If in the buffer there is a real message to be sent, it just grabs this message and sends it. But if there is no message to be sent, the Nym client sends something what we refer to as a loop cover packet. A loop cover packet is a packet which is indistinguishable from real messages. It's a packet which goes through the mixed network and as destination has your own address. So it's like a loop which is coming to you. What it gives you is that if the users have very distinctive patterns of actually communicating and sending and their behavior, once they submit their messages to the Nym client, from the perspective of the adversary, they all behave the same. So as long as a user is online or his Nym client is online, the adversary is not able to infer any information about your behavior, because the only thing which he observes is that you're sending some packets, but he can't tell whether you're actually communicating or are those only cover packets. And the other properties of those loop packets is that it not only hides your sending pattern, but because those loop packets are coming back to you, you're actually also hiding your receiving pattern. So we're obfuscating the sending and receiving patterns. So we're making the traffic confirmation attacks much more challenging to the adversary. But on top of that, the loop cover traffic also allows to detect the active attacks, both for clients and mixes. Active attacks are attacks in which the adversary controls some nodes and is trying to, for example, drop or delay your packets, or he's trying to inject more packets. All this type of active attacks which would allow him to increase his chances to de-anonymize you. And such loop cover traffic allows to detect them. And we actually use this loop cover traffic to measure the quality of service provided by the mix nodes in the network. And we later use that for our proof of mixing, which is a scheme which we use to not only detect the misbehaving nodes and kick them out of the network, but also to reward the mix nodes which are doing a good job in processing the user's traffic. So here you have a quick comparison between the Nym mixnet and other anonymous communication systems. And as you can see, the Nym mixnet is currently the only system which provides you both scalability, strong anonymity properties, support for application of both high and low latencies. But in addition, it also gives you incentives. So while, for example, Tor is fully based on volunteers running the nodes, the Nym approach gives rewards to the operators of the mix nodes. And we also use the decentralized PKI, which is in contrast to the previous designs, which had centralized approach towards that. Our decentralized PKI is in a blockchain, and as was mentioned, we are building this using Tendermint. So let's now look into the Nym credentials, because the Nym mixnet gives you the network level privacy, and this is great, and this really boosts your privacy overall. But imagine you want to use your Nym mixnet to, let's say, read your favorite magazines at New York Times, right? Probably to read them, you need a membership. Now, if you use the Nym Mix network to access the service provider, which gives you access to the New York Times articles, and then you show the membership, which identifies you, probably that's not what you wanted to have. So you would like to have a way to somehow prove that you have a certain membership, or that you're over 18, or some other information about you, that you have some right to use a certain service in a way that does not allow the service provider to identify you. And this is when the Nym credentials come. The Nym credentials are based on the Coconut scheme, but before I will tell you about the properties of the Coconut scheme, let me give you a little bit of a background of what the selective disclosure credentials are. The idea behind this is very simple. Imagine that you would like to go to a bar and you would like to have a drink. You obviously have to prove that you're over 18. So what you need is that you go to the issuing authority and you would like the issuing authority to issue you a credential. A credential might be a passport. And in this passport, you have multiple attributes like your date of birth, your nationality, your name, your surname, and so on and so on. The issuing authority issues you such credential. And now you go to the bar, or you go to any website in which you have to prove that you're over 18. And you're showing this credential to prove that you can have a drink, or that you have a certain membership, or you have certain access. The verifier can verify your credential to confirm that indeed you're over 18, or maybe you have access to a certain service, and so on. So the basic properties of selective disclosure credentials are two. First one is the verifier is always convinced that the credential is valid, so the prover cannot forge a valid credential. And the second property is that even if the issuing authority and the verifier are colluding, so they're both malicious and they're cooperating with each other, they still cannot learn anything more than just the information which you disclosed. So whatever the prover is showing to the verifier, that's the only thing which the verifier is learning. Okay, so the selective disclosure credentials, there are different schemes, but they have a few limitations. The first main limitation among all of them is that they rely on a centralized issuer, which means there's only one issuing authority, which is a problem because a malicious one can just forge a lot of credentials which then can be used, although he shouldn't do that. The second problem or question is that not all of the selective disclosure credentials allow you to issue credential on private attributes without learning the value. So usually you have to go to the issuing authority and show exactly the attributes on which you would like to have credential, and you cannot blind them in any way. And the third problem is that we would like to ensure that if I have a credential and I show it multiple times, so for example, I access the New York Times service provider multiple times, I would like to make sure that the verifier is not able to link those different showings that they come from the same person. And this is where the Coconut credentials and hence the Nym credentials come. So the Nym credentials have a few properties. The blindness, the unlinkability, threshold authorities, non-interactivity, and efficiency. So what it means, first of all, the blindness means that you can ask for a credential on a private attribute, which means the issuing authorities can issue you a credential without learning on what attributes they're actually signing the credential. The unlinkability ensures that even if you have a credential which you show over and over again, those showings cannot be linked between each other. The big thing of the Nym credentials is that we have the threshold authorities, which means there's no more centralized authorities. Instead of that, we have a set of them, and only A subset of them has to be honest and cooperative to issue you a valid credential. Each one of them can issue a partial credential, and then you can aggregate it into one big credential. Also, the authorities don't have to interact with each other. They can issue the partial credentials completely independently. And importantly, the Nym credentials are very efficient, which is important, especially the verification is very fast. And what makes the Nym credentials so good is that they can be used by platforms which support smart contracts, because the threshold issuance allows issuing credentials through smart contracts. So how those two combine is that if I want to access a service and I'm using the Nym network, not only I protect my network level anonymity by forwarding my communication via the mixnet, but also the service provider doesn't really learn my identity. So I can anonymously access services and be anonymous vis-a-vis the service provider, but also any global network adversary. So if you would like to learn about Nym, we have the very detailed documentation, which also can help you spin your own mixnode. Our code is open source, so you can go check it out. If you would like to know more details about things which I was talking here, on Medium, we have a lot of blog posts covering that, even more in detail, so check it out. And if you have questions, you can always send me an email, and I'm happy to answer it. And I think I just ran out of time.
Thank you very much, Ania. Really interesting talk. Thank you for sharing. And yeah, and now I think we have up to the plate Christopher, who's going to be presenting. Christopher, if you can hear this, over to you.
Hi there, can you hear me?
Yes, we can hear you.
Awesome. Never quite sure. All right, let me see if I can share this. So I will give a quick overview of the problem, and then my hope is to have this be a somewhat interactive workshop that may or may not be a success, but we'll try. I have some an online whiteboard tool which I can share with people, so we can work together on the whiteboard to brainstorm solutions to this problem. But first, let me just give a quick overview. Let's do it this way. Cool. Can you see? I realize it's not the presentation view, but I don't think I could find a way to do that. You can at least see the slides. Yes, awesome. So I'm going to talk about fault isolation and privacy in cross-chain shielded transfers, which are two desiderata that happen to be slightly at odds. And my hope is that in this workshop, we can brainstorm some ways to potentially make them a little bit less at odds. So a very basic overview of the problem is that we want to design for a multi-chain ecosystem where there are lots of different chains and many of them have different privacy features. Those privacy features might be based on a sampling circuit like zcash, and that's the model I'm most familiar with, but they might also be based on something like the coconut anonymous credential scheme, which Ania just talked about. And my hope is maybe we can, in this workshop, figure out whether those might even be able to work together. But right now we have multi-chain ecosystem with lots of bridges, but only single chain shielded pools. So maybe there's a coconut credential scheme running on one chain, or there's sapling on zcash, or maybe the sapling circuit is being added to Tezos in an upcoming protocol upgrade. Potentially different blockchains in the Cosmos ecosystem will adopt privacy features. But all of these privacy features right now only exist on one chain. And that means that when you transfer over a bridge, if this is, regardless of whether this is a bridge constructed using ICMP or IBC or some sort of trusted proof of authority, you are losing privacy. So currently, then the advantage of these bridges, or the advantage of having completely transparent bridges, is that they can provide fault isolation by tracking the supply. And that fault isolation requires that the supply tracking be done in public, which means that these need to be unshielded transfers. So my question, or the question I want to brainstorm in this workshop is, can we get some measure both of privacy? So can we combine somehow or the anonymity sets, or partially combine the anonymity sets from multiple chains, so that instead of having a lot of little anonymity sets split all across the multi-chain ecosystem, we can have some one larger one, or at least some partially combined ones, while still preserving this extremely important fault isolation. because usually here we're talking about different chains with different consensus algorithms, different proof-of-stake tokens, different validator sets, different security models, and they don't want to be exposed to each other's consensus fault risk. So I'll get into why those are at odds in just a second, but I also want to note that this is separate for now from the problem of network privacy. Ania just gave a presentation on the Nym mixnet. Network privacy is also absolutely integral. Luckily, it is pretty much orthogonal, and it's probably much easier to combine network privacy for different blockchains than it is to combine the shielded pools, although maybe I don't want to make that statement in high confidence because I do not work on mixnets, but hopefully it's easy. So what I want to work with for this workshop is a pretty abstract model of what a shielded pool is, so that we don't need to get into the nitty-gritty of like the particulars of these zero-knowledge circuits or even anonymous credential schemes, because I don't think it is all that relevant to the problem, except in like the abstract model of what we can and cannot do. So when I say shielded pool, I'm talking about a pool of tokens that have been shielded using, you can think of it using like a sapling style circuit or using an anonymous credential scheme, such that when someone is looking at the public chain, the owner of those tokens is unknown. Transfers within the shielded pool are indistinguishable from each other, except that they're going to this particular shielded pool and that they came in at some timestamp or something like this. If a single chain has a single shielded pool, there will be some supply in what's called the unshielded pool and some supply in the shielded pool. And although you don't know the particular balances users have in the shielded pool, you can subtract, if you know the total supply, just subtract the balance of the unshielded pool from the total supply, and you'll know what the total size of the shielded pool is. So here we're kind of talking very roughly. You could say that the anonymity set is proportional, both to the size of the shielded pool and to the frequency of shielded transfers. How many times per block are people sending transfers to the shielded pool, and you can't distinguish them other than they are a shielded transfer operating on this particular pool. Now, depending on what kind of analysis you're interested in defending against, whether you assume that the adversary has access to network level data about transactions or has partial access to the transaction graph and maybe could eliminate transactions from the set they're trying to search. You may have more specific statistical criteria, but here we're just working at this high level. So the basics of a bridge in this abstract model are that it's a way for two chains to transfer tokens between each other. By default, these bridges are public, meaning that supply is tracked at both ends. For example, this is what's implemented in the ICS-20 standard and IBC, and I believe that ICMP has a close equivalent. This public token tracking means that supply inflation is preventable. What do I mean by supply inflation? I mean that when my chain, let's call it Chris chain, sends tokens to another chain, let's call it Ania chain. Sorry for including you involuntarily in all these examples, but figure it's polite since you were the prior presenter and you have a different privacy technology, which is awesome. So if I send tokens from Chris chain to Ania chain, then I can track how many tokens I've sent when they leave my unshielded pool because that amount is public, and I can ensure that no more than that number of tokens ever comes back. That's what I mean by preventing supply inflation. So even if Ania chain has some kind of consensus fault, the worst that can happen is that the people who transfer their tokens to Ania chain will get them stolen, but supply inflation for Chris token is prevented because I simply block transfers past the tracked amount of supply that originally went out. Of course, however, this means in order to do the supply tracking, that tokens must be unshielded when they are sent over the bridge, which means that the two shielded pools operate in complete separation as if they were two different blockchains with no bridge between them at all. I mean, you could transfer tokens between them through the unshielded pools, but you don't get any additional privacy. So what we want is to find some way to combine anonymity sets from both chains in ways that increase privacy or some degree of privacy for users, but preserve some modicum of fault isolation, which is very important. Then I will share two easy approaches and then some advanced approaches I've thought of so far, and then I want to see if we can brainstorm anything else or brainstorm how, in particular, this might work with anonymous credentials, because I haven't thought too much about that yet. So the default approach, which is sort of what is currently going to happen if no one does anything in particular to solve this problem, is that transfers will happen over unshielded bridges, which provides full fault isolation because the supply can be tracked, but provides no increased privacy. So that's what will happen at the moment in the first version of IBC. As far as I know, same thing with Polkadot. even if there are shielded pools on all these different blockchains, they're going to be completely separate. Then another possible approach, I don't know if anyone's pursuing this, but it would be possible to completely combine the shielded pools in a sort of naive fashion where you ignore consensus fault risk. So then you can combine by combining the node sets and nullifier sets, etc. So then you can run shielded transfers over the bridges, but you don't get fault isolation. And there are some other slight difficulties, but this is at least possible. You just give up fault isolation. So an advanced approach, and I'll pull up a diagram to explain this. Alistair says we'll be doing combined shielded pool as soon as possible. Do you want to join, Alistair? Maybe you have more up-to-date information than I do. I don't know if you can click like.
Hey, so Alistair, if you're in here, you should be able to just share. Okay, yeah, and I actually think we might have. Oh, wait, Alistair says he's going to wait and listen. And in the meantime, I think I have to increase the number of participants. So you go ahead, Christopher, and then if Alistair wants to come up, let me fix that and make sure that's possible.
Gotcha. Okay, so more advanced approaches. One advanced approach, so the key restriction here is that in order to enable shielded transfers over some of these bridges, when we enable shielded transfers, we no longer have access, of course, to the balance transferred in each cross-chain transfer because it's shielded. So what we can do is that we can require that, we could change the circuit, right? So we can require that, maybe the balance goes somewhere else first before it just gets released into the shielded pool in the second chain, and maybe the user has to submit an additional proof of something. What we cannot do, at least not just with zkPs, is encrypted supply tracking. So if we had like some kind of fully homomorphic encryption, then maybe we would have to do this in the circuit. So it's probably going to be incredibly inefficient, but at least in principle, we could require that the user like encrypt their balance, encrypt the balance of the transaction, and then add that homomorphically to some tracked counter, and like, somehow some check needs to be performed over this encrypted value that it doesn't exceed, that the amount transferred back in over some bridge doesn't exceed the amount transferred back out. I am not familiar enough with fully homomorphic encryption to know exactly how that would be implemented, but it's certainly you can't do that just with zkPs because you need to be keeping this like encrypted counter. But one thing you can do with just zkPs is create a sort of temporary purgatory. And this is the best solution I've thought of so far. So I'm hoping we can come up with something better. But it is perhaps a nice point in the trade-off space between the two extremes. So a temporary purgatory means that you basically create what I'm calling this purgatory, and I'll pull up a diagram in a second, which will probably make it more obvious. But I'm calling this purgatory, what I'm calling this purgatory is a place where once tokens are transferred over a shielded bridge, they will sit temporarily. And in this purgatory, so instead of when you transfer tokens over a shielded bridge, you'll provide a zero-knowledge proof that you, burned, that you had the UTXOs to spend on one end, and you'll send them over the bridge. That proof will be verified on the other side of the bridge, but then that new note will not immediately go to the regular shielded pool on the second chain. Instead, it will go to this purgatory. And this purgatory basically means that it will be locked for some period of time. And that period of time could even be dependent on the value of the note because this proof can be done in the circuit. So just for simplicity's sake, say that it will be locked for a day. And during that day, you can't transfer it to the second shielded pool. You would in order to transfer it to the second shielded pool, you need to provide a proof in zero knowledge that some amount of time has elapsed since you created this note, because the timestamp is public, so they're included in the public input, and that proof won't be able to succeed until a day's passed. So for this day, this new note is locked in this purgatory, and no one can see what amount it is. But if there's some kind of consensus fault, let's say it's discovered that the other chain, which sent this zero knowledge transfer, had a fork, then someone can provide a proof of that fork, in regular clear text using some light client verification algorithm to the chain which received this note, and that this purgatory can sort of be locked such that some state variable would be changed on that chain, and then all attempts to transfer from purgatory to the regular shielded pool would fail. So you can think of this purgatory as like this temporary shielded pool with an additional requirement that tokens are locked in it for some period of time. And this doesn't give you supply tracking, but it does give you the ability to deal with, to prevent supply inflation caused by BFT consensus faults, which are detected within a bounded period of time. So this may make particular sense for, bridges like IBC and ICMP, which have the ability to detect faults and handle them in some fashion. Now, this doesn't specify anything about if you have a fork, what do you actually do with these tokens in the purgatory? How do users potentially recover them? That is out of the scope of this kind of design. But at least in the happy path, you end up with, the statistical analysis becomes more complicated because it's not exactly the same shielded pool, but at least after the delay period, they can be transferred to the shielded pool, and you never needed to unshield them along the way, if that makes sense. So I want to pull up a whiteboard here because I think spatial view will help. And theoretically, this whiteboard is one that I can share. So I'm going to paste this link, but I'll also screen share. And if you can open the link, you should be able to okay, I'm going to switch my tab. All right, can you see this? Hopefully, yes.
We can see it.
Awesome. Can you read the text? Is it zoomed in enough?
I can't really read when you're screen sharing it, but I clicked on the link. There you go. That's a little bit better for me.
Gotcha.
Yep.
Thank you. Okay, this is my experimenting with live whiteboards. So here is a spatial rendering of what the simple bridge looks like. We have chain A on the left here, SPA, that's shielded pool A, USPA, unshielded pool A, the unshielded bridge between the unshielded pools, chain B with its own unshielded pool and shielded pool. Does that make sense to people? Do these sort of logical divisions of shielded and unshielded pools make sense? I'll take that as a yes. I can't see anybody.
Yeah, you're getting yeses in the chat.
Awesome. So if we then implement this kind of, I can see people's cursors. That's pretty cool. Okay, so if we implement this kind of more complex purgatory, then what we're going to have here is, we've got the shielded pool, we've got the unshielded pool, we've got the purgatory. This is chain A. That's the purgatory on A. This is the shielded pool on A. This is the unshielded pool on A, which is no longer going to be involved in the bridge. Then we've got chain B over here. We've got purgatory on B. We've got the, yeah, someone's helping me out. That's awesome. Shielded pool on B. And we've got the unshielded pool on B. So, oh man, you already know how to draw these arrows. Whoever the purple cursor is.
Chris,
cool.
Chris, is this a plant? Did you put a plant in there?
No. Right. I thought my PowerPoint presentation would be so confusing that I would need to pull up a whiteboard, but clearly someone has already figured it out. Maybe they just solved the problem years ago and I'm already behind the times. But yes, that is exactly correct. So except that these arrows should not be going from, you drew them to the right place, but not from the right place. So these arrows should be going from the shielded pools, because in this bridge, we don't actually need to touch the unshielded tokens at all. So let me just straighten these out a little bit. So if we think about what's going on here, when you send a, we'll call this the purgatory bridge. So when you send a transfer over the purgatory bridge, you're providing a proof that you've removed the note from one shielded pool. So one shielded pool on chain A, and then you transfer it to this purgatory on chain B. And after some delay period, you can transfer from the purgatory on chain B to the shielded pool on chain B. Just write delay. Then the same holds true for transfers in the reverse direction. So you can create a proof that you've spent some note in the shielded pool on B, send that over the purgatory bridge. You'll get a temporary note in the purgatory on A, and then after some delay period, you can spend that temporary note in the purgatory on A and get a regular note in the shielded pool on A. So you could go all the way around and keep your token shielded. You can see my cursor circling counterclockwise here in the direction I drew the arrows, although you will need to tolerate this delay in transferring from the purgatory to the shielded pool on both chains. So then let's say, let me just copy all this stuff. Let's say a fork happens. What do we do? So let's say we have tokens coming into the purgatory. We're just going to look at one side here. So on chain B, we discover that there's some fork. And at that point in time, we have like, we know, so we don't know exactly what the balance of this purgatory is, but we know like abstractly it's some N tokens. So when we have a fork on chain A, then that proof of fork gets submitted to some light client. And what we do is we draw a I don't know how to quite do this. Well, we get rid of this arrow. So we block the transfer from the purgatory on B to the regular shielded pool on B. We color that red. And that means that these N tokens are locked. So if there was some fork, then as long as we get the fork proof within a bounded period of time, it can't be used to mint tokens because they will, or it can, but they will never get out of the purgatory. Does that make sense?
Makes sense, yeah.
Cool. Do you want to chime in, Anya? Does this abstract model also make sense for like shielded tokens or whatever you call them when created by anonymous credentials? Would you have the same logical separation of shielded and unshielded pools?
Yeah, I mean, it makes sense. I think that would be quite similar, although I'm not really familiar with this topic, so I can't say for sure, but it actually makes a logical sense. So
cool. Sam, you said seems like the end game with this approach is something like a cross-chain mixture that does periodic swaps. Do you want to expand on that? I'm curious.
I'm sure I can expand too much, but if you're considering many chains, then maybe you would want to have a daily or an hourly kind of transfer that had a regular amount or something, and so you end up with this kind of multi-chain mixing service that you enter into.
Do you mean like automatically transferring tokens between the shielded pool just to increase the anonymity set?
Exactly.
Or? I see. So maybe if there's it seems like that's a public good which would need to be subsidized somehow.
For sure.
Like individuals might not want to do that, but
sounds indeed as a good approach.
Right. So I guess one question I have is this purgatory approach, doesn't provide supply accounting, so it can only deal with explicitly detected forks, and it introduces kind of bad UX because users have to wait. You can make that at least dependent on the amount, so you can have the amount is encrypted, it's private, but you can require that when some note is transferred from the purgatory to the regular shielded pool, that someone proves that if their amount is less than 5, an hour has elapsed, or if their amount is more than 500, a day has elapsed, something like that. That works. But it's still, a delay in user experience. Am I missing some way in which you could track supply without like really fancy cryptography, or is it just non-existent? I think Dara, do you want to chime in here? If that's possible. Sounds like you've done something similar.
Just a quick note, Chris. So there's like a little bit of a lag, and Alistair said he can join too. If you stop sharing, I think you have to. I tried to update the settings, but I don't think I can do it while it's ongoing. So when you stop sharing your screen, I think if Alistair or Dara wants to raise their hand or just share, then I can let them in as a moderator, and then they can chime in. And we only have just a note. We only have a couple minutes. And so we'll probably make this the conclusion here.
I gotcha.
Hopefully this works.
I stopped screen sharing, I think.
Okay. All right, cool. Oh, sweet. It did work. Hey.
Awesome.
I went there.
So maybe restate the question that you wanted Alistair to address, Chris.
So the first thing I was saying is if you're forced to use unshielded amounts, people can still split the amount they're trying to send and get some privacy, but you still know the amount that's being gone over. So one solution you might consider is to let's reveal to one person, like a validator who is slashable, my amount, and have them do something crazy. And then if I combine that with splitting, I don't have to trust any one person.
So you would like encrypt your amount to a single validator? Is that the idea?
Yeah. So we have been supervising one with Fatima, a master's student who's trying to do a collateralized bridge shielded, which is also impossible. And we think of doing things like that.
But how does the validator like submit a secondary proof, or they're just slashable if they fail to perform?
They just be slashable
like checks?
For more than the amount if something happened.
I see. But how do they provide like supply alerting to the chain? Or how would they provide, like, let's say the validator doesn't, allows you to double spend because you paid them on the side, if I'm understanding this model correctly. If you encrypted your amount to just them, would they have to publish the amount to the chain in order to, or would someone have to?
They would have to do something about the amount. Like they did have enough collateral to cover it. Like they were slashing.
I see. And their amount, so you get a bound.
So they'd be a bound, but then
amount.
You'd split it. If you had lots, you'd have to split it. If you have lots, you should split it. And then no one would actually.
Sure. Right.
So with that, I got to actually.
It's not going to.
Sorry, Chris, I got to cut you off there because we're out of time for the session. That said, you can create your own session. That's actually possible to do if you go to the Sessions tab. So if anybody wants to follow up on this discussion, you can either go point-to-point video chat, or you can create your own session, and you guys can continue. But we got the next session coming up, ZKV folks. But thanks everyone for watching. Thank you, Chris. Thank you, Anya. Thank you, Sam. And hopefully we'll see you around the event.
Thanks. Ciao.
Take care. Bye.